In this section, we discuss conformal mapping. In the previous part, we considered the meaning of differentiability of complex functions. Here, we look at what it implies for a mapping between complex planes. Consider a complex function w equals f of z. Suppose that this function is complex differentiable at every point in a region D of the z-plane. Then we say that f is analytic in the region D. For each point z in this region, the function gives one value, w equals f of z in the w-plane. If the derivative is not zero, this mapping preserves angles locally. Such a mapping is called a conformal mapping. Now let us look at the meaning of angle preservation. In the z-plane, suppose that two curves, c sub 1 and c sub 2, intersect at a point z sub 0. Let the angle between their tangents at that point be theta. Under the mapping w equals f of z, these curves are mapped to two curves in the w-plane. Let their images be called gamma sub 1 and gamma sub 2. Both image curves pass through the same point w sub 0 equals f of z sub 0. If the mapping is conformal, the angle between gamma sub 1 and gamma sub 2 is also theta. That is, the angle before the mapping and the angle after the mapping are the same. Next, we explain why this happens. Take a small displacement delta z from a point z. Let its argument be theta sub 1. The corresponding change in w is delta w, and let its argument be phi sub 1. If the function is differentiable at z, then for a sufficiently small delta z, delta w is df over dz times delta z. The other direction is represented by delta z prime along the curve c sub 2. Let its argument be theta sub 1 prime. After the mapping, delta z prime becomes delta w prime, and let its argument be phi sub 1 prime. Delta w prime is df over dz times delta z prime. The derivative f prime of z has the argument theta sub 2. Therefore, multiplication by df over dz rotates every small displacement by the same angle, theta sub 2. Thus, the argument of delta w is theta sub 1 plus theta sub 2, and the argument of delta w prime is theta sub 1 prime plus theta sub 2. Now compare the two angles. The angle between delta z prime and delta z is theta sub 1 prime minus theta sub 1. The angle between delta w prime and delta w is phi sub 1 prime minus phi sub 1. Substituting the expressions above, we get theta sub 1 prime plus theta sub 2 minus theta sub 1 plus theta sub 2. The theta sub 2 terms cancel, so the result is theta sub 1 prime minus theta sub 1. This is exactly the original angle between delta z and delta z prime. Thus, the angle after the mapping is the same as the angle before the mapping. This is the reason why an analytic function with a non-zero derivative is conformal. More precisely, let f be analytic in a region D and let z sub 0 be a point in D. If f prime of z sub 0 is not 0, then the mapping w equals f of z is conformal at z sub 0. This is why angles are preserved. This property is called conformal mapping.